Hi, all. Good morning. Today we are going to discuss with another topic. But just before going to that, just I would like to remind what we discussed in the previous class and previous session. So where we started discussion on Spark Ignition Engine Management System, where we maybe mentioned that this engine management system basically consists of three different uh, segments. One is the input segment, one is the control unit segment, and third one is the actuator segment, that is output segment. So where the input segment is comes from various sensors. Based on the sensors input, the ECU will electronic control will unit will analyze the information and provide a proper output to the actuators. So the sensors corresponding to here, maybe if you take an SI engine management system, where we mentioned in the previous session also, like throttle position sensor and manifold air pressure sensor, mass airflow rate sensors, and exhaust gas oxygen sensor, TDS signal and cam position signals, and like engine RPM sensor, engine speed sensors, and engine coolant temperature sensor. So like that we are going to get a different sensors input. Based on that, the ECU will analyze for the best possibility of getting optimum fuel output for injecting into the engine to maintain the stoichiometric air fuel ratio of 14.7 is to 1. So the actuators will be here. One is the fuel injector to supply optimal quantity of the fuel and optimal time, and how many times it has to inject it. So all this still will comes through the ECU instructions, from the ECU instructions. Similarly, at what time we need to ignite the fuel, that is through the ignition timing control. So through that is also through electronic ignition system. For that also the input will comes from the ECU which is present in the engine management system. So in this particular session, just I would like to introduce three important sensors which are responsible for a optimal working of an ECU. Just like we mentioned, it's a closed loop control system. Based on the feedback from these sensors, we can able to adjust the fuel quantity for getting maximum fuel economy, minimal emissions, and maximum power output. That is what we intended to adopt the technology inside the engine. So that's we called as a engine management system. Without meeting these objectives, there is no use of the control system or maybe management system inside the engine. So to address that, sensors input is very important, plays an important role here. So in that particular concept, we are going to discuss three topics like mass airflow rate center, that is shortly we can call it as MAF, and similarly MAP, that is manifold absolute pressure sensor, and EGO, exhaust gas oxygen sensor. Okay, so first we will discuss about the different sensors. As I mentioned here, engine control sensors. So as a part of that, just I would like to mention what are the different sensors which we are going to use in the engine, and we will go into the details of MAP, MAF, and EZO. Just as I mentioned, manifold absolute pressure sensors. Basically, it's a we are going to measure the manifold pressure, and oxygen sensor which is present in the exhaust, and then it can senses the amount of oxygen inside the exhaust. And coolant temperature sensor, it can just measures the temperature of coolant so that it can understand that whether it is cold or hot, or based on that it can assumes that at what uh, mode the engine is operating, either cruise mode, ideal mode, power mode, like that. And throttle position sensor, so measure the throttle position. Based on that I can understand that whether I am operating at ideal speed, that is starting, or cruise range, or maybe power mode. When you are operating in power mode, so the 100% throttle will be open, or maybe when you are overcoming a high load, then the throttle position is 100%. whether I need to go for rich mixture, for lean mixture, that will be decided based on throttle position sensor. And knock sensor, if any kind of unwanted combustion, or maybe unnecessary combustion, or maybe disturbances there inside the combustion, so that limit the power from the inside the engine, that is also measured with the help of knock sensor. And idle speed controller, so it can basically control the idle speed to avoid more fuel wastage due to the during the initial period of the engine, starting of the engine. Similarly, air charge temperature sensor, EGR solenoid, airflow sensor, as we discussed in the last class. So these are the some of the position EGR position sensors, some of the sensors which we are going to discuss in our coming classes. Okay. So the first sensors which I mentioned is the mass airflow rate sensor. So this mass airflow rate sensor, basically its position is shown in this particular picture, which is present in between these two, that is air filter and throttle body, where once the air from the atmosphere is enter into the, before entering into the engine, it enters into a manifold. So where the due to the pressure differential between the manifold and atmospheric air, the outside air will enter into the engine. So during that process, the first step, which I already mentioned in the last session also, which is through the filter, the air is cleaned out to avoid or maybe to eliminate unwanted particles. So those particles will be eliminated in the air cleaner. After that, we are going to measure mass airflow. It's maybe a direct mass flow, or maybe it's maybe a volume airflow rate sensor. So based on the density, we are going to convert into a volume. So but if we can directly measure also mass airflow, since mass airflow rate with the help of mass flow airflow sensor. So here you can see converts amount of air drawn into a voltage signal. Based on the airflow rate, it can converts into a voltage signal, because we can't directly communicate same kind of information, volume flow rate, to the ECU. So the ECU has a particular language, or maybe particular way of mode of it needs a particular mode of communication. That mode of communication we given in terms of an voltage signal, so that ECU will understands based on this voltage, so how much at what load the engine is operating it, that's air volume, to calculate the engine load. So based on the volume flow rate, the ECU assess that at what load the engine is running it. So based on that, it can instruct the ECU how much amount of fuel to inject and when to inject it. So that's why you are able to see mass airflow sensor is very important point while uh, while finalizing the amount of fuel injected and at what time it has to inject into the engine. So maybe I'm not saying that this is only one parameter decides it, but in the weightage of this parameter is very important while ECU determines the amount of quantity fuel to inject it. Okay. So as I mentioned, is directly intake air system between the air cleaner and throttle body. This point I already mentioned right now. So basically this airflow sensor inside the component, if you observe that inside an airflow sensor, basically it's having a hard film structure. This hard film structure, this is hard film structure electronic circuit that is kept inside in a Wheatstone bridge. So the Wheatstone bridge, as we discussed in our +1 and +2, and PW also we come across. So where inside in a Wheatstone bridge, initially when there is no airflow, this Wheatstone bridge is in balanced condition. That means VA is equal to VB. There is no voltage difference between input and output of the voltage. But when airflow is happens, happens across this particular sensor, air from atmosphere, so the hot film structure which is kept inside an Wheatstone bridge, that is RHW, something is hot, it's around 45 to 50 degrees, but outside atmospheric is 30 degrees temperature is present. So due to this pressure difference between the outside atmospheric air and hot film structure, the temperature of this particular hot film structure is going to be vary. So based on the vary temperature. If the volume flow rate is very high, the temperature decrement is very high, from 45 to 40, 45 to 39, like that. If the drastic temperature difference is there, then it can understand that there is a large volume flow rate of air. That means how much the temperature is going to be changed. For example, when the RHW is 45 degrees centigrade hot film structure, then the Wheatstone bridge is balanced in condition, that is VA is equal to VB. But once the volume flow rate of air, or maybe flow airflow is passes through this hot film structure, the temperature of this film structure is varies, so that VA is not equal to the VB. There is a difference will comes into the picture. So that difference will be amplified inside a amplifier, that is given to the, that is given as an output to the AC. So if there is a large volume flow rate is there, then the V1 will be very high, that is communicated to the ECU. If the volume flow rate is of air is very low, then the temperature drop is very low, so that then in the ECU, the voltage signal which is V1 as an output after the amplifier is goes to the ECU, then the ECU will understand that there is a low load condition. So in order to maintain the temperature of this hot film structure always, so after the amplifier, whatever the voltage is there, VA minus VB, that is the difference will goes to the VC, that is further back supplied to hot film structure to maintain that temperature. Otherwise it's not it will not work. The MAF sensor needs some kind of current or maybe the power to maintain this hot film structure at the same temperature. So that's why you can try to see initially the hot film structure is kept at some temperature. Once the engine is starts, based on the airflow rate, at what condition the engine is running, based on that the temperature will be varies, and the difference in the voltage difference, or maybe the difference in the imbalance in the Wheatstone bridge causes or maybe generation of a particular voltage VC, that is amplified after the Wheatstone bridge, then the VC will be communicated to the ECU. That's why you can try to understand this particular MAF sensor working. If the temperature drop is very high, voltage is very high. If the temperature drop is low, then the voltage, output voltage from the Wheatstone bridge is low, so that the ECU will understand that low load condition. That's why you can see intake air temperature as a part of housing assembly. The hot fill is maintained temperature in relation to the intake air temperature by ECU. So if more air flow rate is there, then more drop in temperature. That's why you can the art film maintain temperature in relation to the intake air temperature by ECU. That's point you need to understand here. So same thing I mentioned here in terms of explanation. You can try to see the hot film incorporated in a Wheatstone bridge that I mentioned, and 3 R1 and R2 and R3 and hot films element having resistance RHW. When there is no airflow, so R1 and R2 are chosen such a way that voltage and VAB are equal. As the airflow across the hot film, the heat is carried away by the film by moving air. Because of the temperature difference of between hot film structure and moving air, there is a some amount of air is carried away by the air from the hot film structure. The amount of heat carry varies in the proportion to the mass airflow rate or maybe volume flow rate. If the more amount of air is flowing, more temperature will be carried away, so that more temperature drop will be occurs. So film, the heat lost by the film to take cause the resistance to the filmy vary, which causes unbalance the circuit, thereby producing the input voltage to the amplifier. So that's the only thing you can understand it. If more airflow rate is there, then more temperature drop or maybe more temperature is carried away by the intake air, so that temperature drop is very high, so that you can understand that more voltage signal to the amplifier. There is unbalance in the Wheatstone bridge and more voltage will be generated. That you need to understand here. So how the mass airflow rate sensor looks like? This is a mass airflow rate sensor as you are seeing from here. So here also you can see, when you are able to cut down this part, you can try to see this particular part to maintain this Wheatstone bridge here basically. So that's the basic details about MAF sensor. Okay. So here also I mentioned the output of amplifier is connected to the bridge circuit, provides the power for this circuit. So the amplified voltage changes the resistance in a such a way that to maintain the fixed hard film structure related to the inlet temperature. So the amplified voltage changes the resistance in a such a way that to maintain fixed hard film structure related to the inlet temperature. So that means once you get a imbalance through the voltage imbalance or maybe temperature resistance imbalance, then voltage is generated in the Wheatstone bridge. That Wheatstone bridge voltage is supplied back again to the hard film structure to maintain the temperature. If you do not maintain the temperature, then there is no point to operate the sensor. So we need to maintain always the temperature difference between hard film air, hard film structure and atmospheric air. If you do not maintain it, then the sensing information is low and the wrong information will be communicated to the ECU. That should we need to avoid it here. And similarly, the second sensor is a MAP sensor, that is manifold absolute pressure sensor. So this is basically very important because in the first case, by using mass air flow rate sensor, we are going to calculate the fuel intake based on the direct direct method. Indirect method is not, it's basically a direct method for calculating the uh, fuel intake. So whereas when you are going with a mass absolute that is manifold absolute pressure sensor, we are going to go for indirect method. Based on it, we are going to calculate the amount of fuel which we are going to inject into the engine. So this indirect method basically uses two sensors, that is manifold absolute pressure sensor and also uh, manifold air temperature sensor. That is also we discussed when we mentioned about engine management system, indirect way of measurement for the fuel flow. So that's why you can see this manifold pressure sensor is senses the engine load. So in case of MAF also we mentioned that if the more air flow rate is there, then more heat is carried away by the air, so that more voltage is generated due to the large temperature drop. And it can understood that ECU can understand that based on the large voltage, it can understood that large load, engine load, assess the engine load. Similarly, manifold absolute pressure also will indicates the engine load. That's a thing. So similarly, the MAF sensor is present in between the throttle body and air cleaner, whereas this MAP sensor is present inside the intake manifold. So this we discussed in the last class also. This is basically air filter. Then we have a manifold will be present like this. This is manifold where again it will be goes. So here we have a throttle position. We have a MAF sensor, and here also we have throttle position sensor, whereas MP is correct here, MAP is connected here, MAP manifold air pressure. After these two sensor MAF and TPS, then manifold absolute sensor is present over the intake or it is mounted on the intake manifold. That's the point. And so basically it is okay, so it monitors basically the pressure in the intake manifold and the outside reference pressure, as I discussed and I already mentioning. So due to the pressure differential only between outside atmospheric air and intake manifold pressure, or maybe the vacuum pressure, or maybe engine pressure, inside that there is a vacuum pressure is present initially. So due to this pressure differential only, outside atmospheric air will be enter into the engine. So if the vacuum pressure or maybe the pressure difference between inside the manifold and outside atmosphere both are equal, then there is no air drawn will be occurs. Always there should be a difference in the vacuum. So how this vacuum is created? Based on the throttle position opening. If the throttle position is open only 20%, then more vacuum is there inside the manifold. If the throttle position is 30%, 40%, 50% and 100%, as the throttle opening is increases, then the vacuum pressure is goes down. That's why you can try to see based on the manifold air pressure, manifold absolute pressure. So if the manifold absolute pressure sensor detects any kind of engine load, that is based on the vacuum pressure. If the vacuum pressure is very high, then engine understood that, maybe the EC understood that the vehicle is going at a low load condition. If there is no vacuum pressure inside the manifold, then the ECU can understand that the vehicle is, or maybe the engine is operating at high load condition, because the throttle opens 100% at that time condition. So the sensor responds to the vacuum inside the manifold and generates the voltage signal accordingly. If the vacuum is very high, then voltage signal is very high, then it is sent to the ECU. The input to the sensor adjusted using adjusting the fuel mixture and ignition timing according to the changes. So please try to understand that if this particular sensor, the input of the sensor is used, that means the absolute pressure sensor is used, I already mentioned, to adjust the fuel air mixture as well as the ignition timing. If based on this sensor input, the ECU can understand that at what engine load the engine is operating, that based on that it will supply the fuel. That's the point you need to understand here. And how it will be looks from this picture, you can try to see. Before going to this picture, you can try to see. So this is intake manifold pressure sensor. So where we are going to use a silicon chip. This silicon chip is present in a such a way that, exposed in a such a way that, one is towards the intake manifold. This is intake manifold side. So this is this is intake manifold side, and this is an outside atmospheric air. So you can try to see the intake manifold side always a vacuum chamber here. One side of this particular silicon chip is exposed to basically a vacuum side, and another side is an outside atmospheric air. If there is a large difference is there, then silicon chip is flexes, that means it is expands. So in the next picture I will show how it will be looks. Basically this is very simple way. So when there is a wide open throttle is there, intake manifold pressure, there is a high pressure, then at the time you can try to see the silicon chip and the vacuum chamber. Due to the one side of, so you can try to see this is the silicon chip, and one side of the chip is reference pressure, either a perfect vacuum or maybe calibrated pressure depending upon the application. On the other side is the pressures to be measured. So you can try to see this is vacuum chamber I am going to expose. This is placed inside the cylinder, inside the sensor itself, that's a vacuum chamber. And other side is if it is a high pressure, when you are open a wide open throttle condition, inside the manifold the pressure is equal to atmospheric pressure, so that the difference is very high, so that we can see a large voltage, because it is flexes, the silicon chip is flexes very heavily. Similarly, when you are operating same at the low pressure side or ideal condition, the throttle is opened very low, so that the vacuum chamber and inside the manifold there is vacuum is present always, so that the difference in the pressure is very low on the both the sides. If you compare on the both the sides, the pressure is difference is very low at the ideal condition. But when you are opening at idle wide open throttle condition, the pressure inside the manifold is equal to the atmosphere, because the throttle is open 100%, so that the pressure inside the manifold, the pressure at outside atmosphere, both are same, so that the difference between the reference pressure, that is vacuum chamber pressure, and the atmospheric pressure is very high, so that the voltage is also very high. Why the voltage is very high? Because the silicon chip flexes heavily. When it is flexes, then the voltage generation is very high. Why we are converting this expansion into voltage? Because the ECU will understand the information only in terms of the voltage signal only, not any other form. Okay, so that's a basic thing. So similarly, if you go to the back, so you can try to see either directly in this is either directly mounted on the intake manifold, mounted on the high in the engine compartment, and connected to the intake manifold with a hose, with vacuum hose. Vacuum hose is nothing but a pipe. So basically it is connected, or maybe you can try to understand, one end is connected to your reference chamber, and another end, the silicon chip, is exposed to another side, is exposed to the intake manifold pressure. If the pressure difference is very high, voltage generation is very high. Same explanation which I quoted here. Silicon chip changes its resistance with changes its pressure. If the when the silicon chip flexes with the changes in the pressure, the electrical resistance of the chip changes. This change resistance alerts a voltage signal. So the MAP sensor highest when the intake manifold is pressure is very high. Ignition key is on, engine off, when the throttle valve is suddenly open. So then the voltage signal is very high. So is lowest when the intake manifold pressure is lowest, the deceleration is throttle closed. That's I already mentioned. So when the throttle is closed, basically at idle conditions where the opening is very low at that time. When there is a wide open throttle condition, that is throttle suddenly open or maybe open 100% at the time, the voltage signal is highest and lowest is this much. Clear? And third sensor which I am going to discuss is the AGO sensor, that is exhaust gas oxygen sensor. So this is very important sensor inside entire engine management system, because it's basically a in order to have a closed loop control system. That means basically both are present, either that means the previous sensors, that is MAF and MAP, both are used to calculate the engine load. Whereas once the engine load is calculated, based on that it will instruct the ECU to inject the quantity of the fuel, and quantity of the fuel and how much time it has to be open. Once it is injected, then the engine generates the power and generates the emissions, also exhaust emissions, where the exhaust gas oxygen sensor used here to calculate amount of oxygen which is present inside the exhaust. That you need to understand it, amount of oxygen which is present inside the exhaust. If the oxygen levels are present at particular level, then it can understand that, analyze the information whether the injected mixture is working in lean condition or maybe the engine is working under rich condition. It can decides that. Clear? So for before going to details about this sensor, you can try to see the position of this sensor. So the sensor is present here after catalytic converter and before catalytic converter. So two oxygen sensors are present here. So basically we will see the input from the before catalytic converter, which is transferred to the ECU, and after also we can given to the ECU. This is basically used to understand the catalytic converter performance. This part we will discuss in another time, but you can understand that at this junction the catalytic converter performance basically analyzed based on the exhaust gas oxygen sensor that is placed after downstream of the catalytic converter, before catalytic converter, which is basically used for the powertrain control module to analyze the information about whether supplied mixture is correct or not. Clear? So that's why you can see the fuel injection feedback loop, that is nothing but closed loop, is happens when this oxygen sensor gives a proper information. That's why it is very important. And this sensor name is also called lambda sensor. It is located after the catalytic converter and before the catalytic converter also. So we are going to take this is input as a prime. So based on the AGO sensor signal, the ECU will adjust the amount of fuel is injected into the intake gauge stream. So for example, before going to the details, so when oxygen sensor gives the oxygen levels are very low. So when oxygen levels are very low, when you not supply enough amount of oxygen during the intake process, that means when you supply more rich mixture, that means more fuel quantity and less air quantity, that means the amount of fuel supplied is more than the required for complete combustion, then it's called rich mixture. If amount of fuel is supplied less than the required for complete combustion, then it is called lean mixture. If rich mixture is supplied, we are already supplying less amount of air than required, so that there is no amount of oxygen left in the exhaust. So when there is no amount of oxygen left in the exhaust, then corresponding voltage is generated, that is supplied to the powertrain control module. Similarly, if you supply more amount of oxygen than required for complete combustion, then it's called lean mixture. So that even though combustion is happened, some amount of oxygen is present inside the exhaust, so that it will be sensed by the oxygen sensor, that is again passes through the even pass the information is passes to the exhaust gas oxygen sensor. So here you need to understand that one of the important parameter in the exhaust, so many gases are present, like we can say CO, HC and NOx. Sometimes another emissions also present, majorly this, along with that CO2, so and O2. So out of these exhaust gases, I need to only identify these oxygen gases, oxygen molecules. Then only I can give a proper information to the ECU. So how much amount of oxygen which is present inside the exhaust. So out of these gases, whatever the sensor I am going to use for EZO, as like EZO, so it should attract only oxygen molecules. Remaining thing it should goes away. So the sensor which is having a ZrO2, zirconium dioxide and platinum kind of elements, so those will attract the oxygen molecules if any oxygen is present inside the oxygen, so that it can give the information to the ECU. So how we can see, same the exhaust is located in the exhaust manifold. So the sensor monitor the amount of unburnt oxygen is present in the exhaust, that I already mentioned. So when the fuel mixture is rich, almost oxygen is exhausted during the combustion. I already mentioned what is mean by rich mixture. That means enough amount of oxygen is not present inside the mixture, more fuel than required, so that then the mixture is called rich, so that little unburnt oxygen is left out in the exhaust. Difference in the exhaust gases levels and the reference is the outside atmospheric oxygen creates an electrical potential which causes the sensor to generate a voltage. Clear? If the difference is very high, that means during the rich condition very little amount of oxygen is present in the exhaust, and the outside atmosphere more oxygen, that is the reference. With respect to the reference, the oxygen inside the exhaust is very low, so that the voltage signal is very high. That will be communicated to the ECU, and the ECU will understand, or maybe PCM will understand that it's a rich mixture. Similarly, when you supply a lean mixture, then the difference between the outside atmospheric air and the inside the exhaust, the oxygen level somewhat high, so that the voltage signal is low, so that the engine understand that it's a lean mixture. If there is no amount of oxygen is present inside the exhaust, then it can understand that it is a stoichiometric air fuel ratio. That's what we intended actually. Always it should be near to the stoichiometric air fuel ratio, or maybe stoichiometric air fuel ratio. That means always we can ensure that zero amount of oxygen which is present inside the exhaust. Clear? So the sensor output will be very high if the fuel is mixture is rich, and the sensor output is low when the mixture is lean. That's point you need to understand here. So based on this information, check the quality of fuel mixture to make the changes accordingly. So if the rich mixture is supplied, or maybe lean mixture is supplied, so that is not acceptable here. So or maybe acceptable sometimes. For example, when you are operating in the cruise range, we need to ensure that the mixture should be in lean condition. And when you are operating in a power range, then I need a rich mixture. So that you need to understand. Based on that, the EC will check the quality of the fuel, how much amount of the fuel it has to inject it. So how it will be looks, this basically an oxygen sensor. This is connected to a power plug to supply the power, or maybe to generate the voltage. So you can try to see, this is outside atmosphere, and this is basically exposed to the exhaust this end. So where I can supply a different exhaust gases, different flow rates. So where we having a platinum electrode with the help of zirconia element. So this platinum electrode and zirconia element ZrO2. So when oxygen flows, this ZrO2 will attract the oxygen molecule and supply to the platinum electrode. So this will compares about the voltage. So here the temperature of exhaust gas is in the order of 1000 degrees centigrades. To avoid, or maybe to withstand the temperature, we are going to keep with a ceramic coating. So this, when they have a ceramic coating, then exhaust gas temperature will be uh, is withstand by this particular sensor. So that based on, even though it is attracted oxygen molecules, that is compared here between outside and atmospheric air and generates a voltage. So how it will be the main components of VGO sensor is the zirconium dioxide and platinum electrode and heater. So this zirconia element, as one end is exposed, as I mentioned, one end is exposed to the reference pressure and another end is exposed to the atmospheric air. So each side's platinum electrode is connected to the zirconium oxide element. Okay, so tendency to attract the oxygen ions which accumulate on the ZrO2 surface just inside the platinum electrodes becomes electrically more negative than the exhaust gas side. So when more oxygen levels are present, then it becomes a more negative, that becomes a more voltage. So the polarity of this voltage is positive on exhaust side, so negative on the air reference side of the ZrO2. You can try to see in this picture again, back. Can try to see. So ZrO2 having two electrodes, that is platinum electrode which is exposed to the atmospheric side, and similarly this platinum electrode is exposed to the atmospheric side. Inside this platinum electrode we have a zirconium solid electrolyte, that is zirconia element ZrO2, which can attract the oxygen molecules, and this is, if the more amount of oxygen is present, then it becomes a more negative, or maybe when more amount of oxygen present is more negative. That's why you can see atmospheric side becomes more negative compared to this side. Due to this polarity difference, the voltage is created. If more amount of voltage is created, then you can understand that it's a rich mixture. If there is no more voltage is generated, that means more polarity difference, if you do not observe, it is a lean mixture. That's you need to understand from this point. Okay, so similarly, if the remaining sensors like throttle position sensors and coolant temperatures and engine RPM sensors, like that other sensors also we will continue in the next session. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.